Hello students, welcome to 13th lecture of electrochemistry. In previous lecture we discussed about conductivities of electrolytic solution. In this lecture we are going to discuss about batteries, that means cells which we are using in regular life. Any battery or cell that we use as a source of electrical energy is basically a galvanic cell, where the chemical energy of redox reaction is converted into electrical energy. However, for a battery to be practical use, it should be reasonably light, compact, and its voltage should not be varying appreciably during its use. That means if you are using a battery which varies its voltage too much, then practically you cannot use it. As for example, suppose you are using a simple cell in a wall clock, and the voltage coming out of it has very large difference in overall time period usage. Then it may be in certain period our clock, because of high voltage, will run faster. At certain period, because of low voltage, it will run slowly. That means it will show us incorrect time. So it is not acceptable. Similar situation can be occur with different devices as well. So voltage should not vary during the usage. Then it should be compact and it should be lightweight as well. Now assume a galvanic cell which we learn first, copper zinc cell. So it uses liquids in two different containers. Now assume a battery in today's life which has these type of liquid containers in it. Then we cannot use it practically because transportation of such things are comparatively complicated. So that means you cannot use it. There are mainly two types of batteries and we are going to discuss them step by step with suitable examples. So first one is primary batteries, and this example is very common for us. In primary category we have a dry cell which we use in our regular life as a cell used in clocks or remote controls and etc. Okay, so in torchlight we use these type of cells, comparatively bigger in size. In clocks we are using comparatively smaller sized dry cells. In remote controls we are even using smaller size AAA batteries. So these are few examples, and here is the structure of this cell. So this battery contains zinc cup which behaves as anode, and we have mixture of MnO2 with carbon black and NaCl in paste form, which will behave as electrolytic solution, and then we have carbon as a cathode. So this is our cell formation, in which we have anode, cathode, and our electrolytic medium which connects both of them. So in this cell both of them are direct in contact. Both of the electrodes are present in same electrolytic solution, so no need to use salt bridge. If you are using two different containers for anode and cathode, then you have to use salt bridge to complete the circuit, but these two are in the same electrolytic solution, so no need to use it. In the primary batteries, the reaction occurs only once, and after use over a period of time, battery becomes dead and cannot be reused again. That means this is the problem with primary cells, they are one time use. And we know that we regularly use these type of primary batteries, and then after batteries are dead, we throw them. The most familiar example of this type of battery is dry cell, known as Lec-13 cell after its discoverer, which is used commonly in our transistors and clocks. The cell consists of zinc container that also acts as anode, and the cathode is carbon, and they are surrounded by powdered manganese dioxide and carbon. The space between the electrodes is filled by moist space of ammonium chloride and zinc chloride. The electrode reactions are complex, but then we can write them approximately as follows. So here two different reactions are mentioned. Actual reactions are complicated, but we are just concentrating on redox couples, that means species which is being reduced and oxidized. So on anode, zinc is oxidized in Zn plus 2 ions, and on cathode we have MnO2, NH4 plus and electron, which gives us MnO, OH and NH3. So let us try to find which of them is being reduced. So oxidation state of Mn before reaction, here we have plus 4. Oxygen will be minus 2 And in NH4 plus, nitrogen will be -3 and hydrogen will be +1. Okay, so these are the initial oxidation states. After reaction, we have MnOOH, that means OH contains -1 oxidation state, oxygen contains -2, so M must be +3. And in NH3, again same oxidation, -3 and +1 will be observed. So oxidation state of oxygen, hydrogens do not change, and nitrogen, they do not change, but manganese do. So +4 to +3. So Mn is being reduced from +4 oxidation state to +3. So actual redox couple will be zinc and MnO2, in which MnO2 is being reduced from +4 to +3. In the reaction, the cathode manganese is reduced from +4 to +3 and ammonia is produced in the reaction from the complex Zn plus 2 gives Zn NH3 4 times 2 plus. The cell has potential nearly 1.5 volt, and you can check it yourself. Use a battery which is already present in your remote controls or in clock and try to find voltage mentioned on it. Then we have mercury cells, which is also known as button cells. They are used in some toys and our wristwatches. So wristwatches, we know that has very small design, so we have to use some smaller sized batteries for them as well. And we use button cells, which is known as mercury cells, which is mentioned in figure 3.9. So here we have an image of our mercury cell, which is also known as button cell, because they are very small in size and round in shape. That's why they are referred as button cells as well. So we have anode and anode cap and separator, gasket and cell can, etc. in this structure. Now we are going to discuss about the chemicals used in this cell. So these cells are suitable for low current devices like hearing aids, watches, etc. Consist of zinc and mercury amalgam. Amalgam, that means paste like substance, as anode, and a paste of HgO and carbon as the cathode. The electrolytes is a paste of KOH and ZnO. The electrode reaction for the cells are as mentioned. On anode, zinc mercury amalgam with 2OH minus gives ZnO H2O and releases 2 electrons. On cathode, HgO, H2O and 2 electrons will generate mercury metal in liquid state and 2OH minus ions. And overall reaction will be zinc mercury amalgam plus HgO gives zinc oxide and mercury metal. Because it is liquid, that's why Hg is mentioned with L symbol, which represents it is liquid. So the cell potential is approximately 1.35 volts and remains constant during its life, as the overall reaction does not involve any ion in the solution whose concentration can be changed during the lifetime. So main issue is with concentration change. As the concentration changes, reaction slows down. As the concentration decreases, reaction becomes slower, and that's why less number of electrons will be produced, resulting in lower voltage. But if no concentration changes are involved, as we can see in this case, either we have solids or paste forms of the substance or reactants used in the reaction. That's why we can consider them as a solid, and no concentration change for the solids are considered in the reaction. That's why we use unity. So that's why no change in concentration, that means no change in voltages. Then we have secondary type of batteries, which are rechargeable and more complex than primary cells. A secondary cell after use can be recharged by passing current through it in the opposite direction so that it can be used again. That means by passing electrical current in opposite direction, we are actually reversing the reaction. And because of reversal of the reaction, we are charging the battery. A good secondary cell can undergo a large number of discharging and charging cycles. The most important secondary cell is the lead storage battery mentioned in figure 3.10. And this type of lead storage batteries are used in our vehicles. So as we can see, we have one anode and a cathode and inside look of our lead storage batteries. So as we can see, we have different plates of metals separated by some divisions, and liquid is filled in it, which is sulfuric acid solution. Okay, so in this case we have positive plates of lead grids filled with PbO2 and negative plates filled with lead grilled and spongy lead. Okay, so we have mainly lead and H2SO4 solution in this case. So PbO2 and H2SO4, these are the main components of our battery. So maybe you know that we have to fill pure water or distilled water in these batteries over time, because H2O will react with lead present in it, and eventually it will convert into sulfuric acid. And sulfuric acid, that means it is more reactive, so it is charged. If the concentration of sulfuric acid is higher, then it represents battery is charged, and if concentration decreases, then battery will discharge. So by adding the water, we are actually adding reactant for the reversal reaction or charging reaction. When we pass the electricity, water will participate in reaction, and with the help of water, sulfuric acid will be produced during the reaction and battery will be charged. So let us talk about the details. So these batteries are commonly used in automobiles and inverters. It consists of a lead anode and a grid of lead packed with the lead dioxide as a cathode, and 38% solution of sulfuric acid is used as an electrolyte. And overall reaction will be, on anode, lead solid will react with SO4 2 minus ions from the H2SO4, and it will produce PbSO4 and releases 2 electrons. On the cathode, PbO2 will react with SO4 2 minus and H plus, that means it will react with H2SO4, and by consuming 2 electrons, it produces PbSO4 and 2H2O. So notice, in both of the case, anode and cathodic reaction, our main products are same, which is PbSO4. Now overall cell reaction consists of cathode and anode reaction as follow: Pb solid and PbO2 with H2SO4 gives PbSO4 and water. So as we can see, we have pure water produced during the reaction, so it will be our product during the discharge process, and it will be our reactant during the charging process, as we are going to discuss it. Now on charging the battery, reaction is reversed and PbSO4 on the anode and cathode is converted into Pb and PbO2 respectively. So that means when we charge our battery, actual reaction will be reversed. That means you can use same reaction in opposite direction. That means 2 PbSO4 and water with help of external electricity will produce Pb solid, PbO2 solid and H2SO4. So it is charging process of our battery, and when we use the battery, same reaction will be observed. Pb solid, PbO2 with H2SO4 gives PbSO4 and water. Okay, so this is discharge and charging process of our first secondary cell lead storage battery. Now the another important secondary cell is nickel cadmium cell, which has longer life than the lead storage cell but more expensive to manufacture. So these type of cells are comparatively more compact than lead storage cells, but as mentioned, they are comparatively costly. So expensive to manufacture, that's why it will cost us more. But in certain cases we use these type of cells, as for example in cameras. Okay, so cameras uses pencil cells which are rechargeable, and actually these cells are nickel cadmium cells, as we can see in this case. So we are not going to go in details for this cell functions or cell reactions, but overall discharge reaction is as mentioned. CD solid with NiOH thrice gives CDO and NiOH twice with water. So this cell has multiple different type of plates separated with separator, and they will gives us comparatively good life and rechargeable times. Then our next point is fuel cells. These are very important type of cells. Production of electricity by thermal plant is not very efficient method, and it's major source of pollution. We can say that these type of procedure to produce electricity has only 25 to 30 or a maximum up to 35% of efficiency. So it is very poor efficient reaction, and it produces lots of pollutants. So when we burn coal to produce thermal energy, and then we can convert this thermal energy into electrical energy, during these conversion processes, each time when we are converting form of energy into another form, some of the energy will be wasted. So as these steps increases, more and more wastage we have to deal with. So in such plants, the chemical energy, heat of combustion of fossil fuel, coal, gas or oil is first used for the converting water into high pressure steam, and this is then used to run turbine to produce electricity. That means we are discussing very old technology in which we are using steam engines. Okay, we use these type of engines in trains in earlier times, and even in cars. Earlier cars uses this type of steam engines which uses coals or wood as a burning material or as a fuel, and then it will heat our water, which expands into steam, and it will provide energy to wheels. So same technique will be used, and we are still using it to produce electricity. We know that the galvanic cell directly converts chemical energy into electrical energy, and that's why it is more efficient. So as these steps decreases, wastage of energy also decreases, and higher number of steps, that means more wastage. It is now possible to make such cell in which reactants are fed continuously to electrodes and products are removed continuously from the electrodes compartment. That means second problem with our cell is, as the reaction proceeds, the reactant's concentration decreases and product concentration increases. Now if you decrease the concentration of reactant or if you increase the concentration of product, according to Le Chatelier's principle, reaction will slow down. But if you are continuously adding reactant and if you are continuously removing products, that means you are increasing the concentration of reactant and decreasing the concentration of product. That means as per Le Chatelier's principle, we are increasing the rate of reaction. So we are going to do this in our fuel cell. Galvanic cells that are designed to convert the energy of combustion of fuel like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cell, and these fuel cells have very large importance in future. Here is a simple example of a fuel cell which uses hydrogen and oxygen mixture as a fuel which produces energy in term of electricity, and as a waste material we have H2O, that means pure water. So this reaction is very efficient and pollutant are zero. That means it is completely non-pollutant, very highly efficient, and output water or extra material will be used for drinking purpose as well. That means we are using this type of cells in our rockets or space shuttles which uses hydrogen and oxygen powered rockets, and it produces water which can be used for drinking purpose for astronauts. So it is one of the most useful fuel cell, and reaction of hydrogen with oxygen forms water. The cell was used to provide electrical power in Apollo space program. That means imagine we are using very high efficient fuels which produces zero pollutants and pure water which can be used for drinking purpose by astronaut, and it means we can reduce mass of rocket. That means we can reduce the weight of our rocket or space shuttle, because water is very necessary for humans, and we have to carry it if we are doing manned missions in space. But if we are using hydrogen powered fuel cells, then it will produce the water. That means no need to carry it separately. In the cell, hydrogen and oxygen are bubbled through the porous carbon electrode into the concentrated aqueous sodium hydroxide solution. Catalysts like finely divided platinum or palladium metals are incorporated to electrodes for increase the rate of electrode reaction. The electrode reaction are as given below. So here we have simple reaction. Oxygen when combined with H2O, it consumes 4 electrons and gives 4OH minus. H2 gas combines with OH minus and produces 4 moles of water and releases 4 electrons. So overall 2 moles of water will be consumed and 4 will be produced. So net 2 moles of H2O will be produced. So this is our net reaction. 2 moles of H2, 1 mole of O2 gives 2 moles of H2O. So this is our waste material. This cell runs continuously as long as the reactants are supplied. The fuel cell produced electricity with an efficiency about 70% compared to the thermal plants whose efficiency is about 40%. This is the maximum limit. With latest technology we reached up to 40% of efficiency. In earlier days it was even lower than this. That means from the 100 gram of coal you are absorbing amount of energy is equal to 40 grams of coal. 60% is wastage, and wasted means pollutant. So that's a main downgrade for our traditional fuel. There has been tremendous progress in the development of new electrode materials, better catalysts and electrolytes for increasing the efficiency of fuel cell. These have been used in automobiles for an experimental basis. The fuel cells are pollution free, and in a view of their future importance, variety of fuel cells have been fabricated and tried. That means in this point it is mentioned that we are trying to use hydrogen powered vehicles, which is already in development and in testing processes in India and other countries as well. They are more efficient, less pollutant. Even electrical vehicles produces waste material after certain period of their lifetime. That means batteries which are being used in electrical vehicles are almost non-decomposable. We cannot decompose them or we cannot recycle them. So we have limitation and their pollution levels are quite high. That means during the use of battery it won't produce any pollutant, but after the batteries are useless or they become dead, we are talking about secondary cells rechargeable batteries. When they become dead, we cannot recycle them. They produce comparatively high level of pollution. Now our last point is corrosion, and corrosion is also one type of electrochemical reaction. Corrosion slowly coats the surface of metallic objects with oxide or other salts of the metal. The rusting of iron, tarnishing of silver, development of green coating on copper and bronze are some of the examples of corrosion. It causes enormous damage to buildings, bridges, ships and overall objects made by metal, especially that of iron, because iron is very reactive material and we use it widely. Okay, so because it is cheap and strong, but it has some downgrades as well. In corrosion, metal is oxidized by loss of electron to oxygen and formation of oxide. Corrosion of iron, commonly known as rusting, occurs in presence of water and air. So these two are very important for oxidation reaction of iron, which is production of rust. The chemistry of corrosion is very complex, but it may be considered essentially as an electrochemical phenomenon. At a particular spot, as mentioned in figure 3.13, of an object made of iron, oxidation takes place and that spot behaves as anode, and we can write the reaction as follows. So anodic reaction will be 2 moles of Fe solid produces 2 moles of Fe2 plus and releases 4 electrons, and the potential of this reaction is minus 0.44. So reduction potential of Fe is negative, that means it will oxidize. Electrons released on anodic spot move towards the metal and go to another spot on the metal and reduce oxygen in presence of H+, which will be believed to be available from H2CO3 formed due to the dissolution of carbon dioxide from the air into the water. That means carbon dioxide gas has comparatively some low value of solubility in water, but it will dissolve up to some extent in water. Our atmosphere contains some amount of carbon dioxide gas and moisture as well. So when this moisture, that means H2O, comes in contact with CO2, they will produce carbonic acid known as H2CO3. That means it is directly combination of H2O plus CO2. and it is also known as carbonic acid. And when one very common example of carbonic acid is our soda. Okay, so soda is actually pressurized carbon dioxide gas into water, and it will increase solution of carbon dioxide into water. Because of higher pressure we have more concentration of carbon dioxide, that means more solubility. So this type of H2CO3 or carbonic acid will provide H plus in the reaction. So hydrogen ion in the water may also be available due to the dissolution of other acid oxides from the atmosphere. This spot behaves as cathode with the reaction as follow. Oxygen with 4H plus and 4 electrons gives water molecules, and for this reaction reduction potential is 1.23. So overall reaction will be 2Fe plus O2 with H plus gives 2Fe2 plus and H2O, and for this reaction cell potential is 1.63, which is positive. That means this reaction will be spontaneous. The ferrous ion are further oxidized by atmospheric oxygen to ferric oxide, which comes out as a rust in the form of hydrated ferric oxide Fe2O3 XH2O, and the further production of hydrogen ions. So prevention of corrosion is prime importance. It is not only saves money but also helps in preventing accidents such as building collapse, bridge collapse, and failure of key component due to corrosion. One of the simplest method to prevent the corrosion is to prevent the surface of the metallic object to come in contact with atmosphere. By coating them we can do it, by coating them with help of paints and red oxides. This can be done by covering the surface with paint of some chemicals, example bisphenol, and another simple method is to cover the surface with other metal more reactive than our actual metal, SN, ZN, etc., that are inert to react to save the object. And so inert, that means they won't allow our actual metal to react until they are being consumed. An electrochemical method is to provide a sacrificial electrode for another metal like magnesium, zinc. They are quite reactive metals than the iron, which corrodes itself but saves the object. So these are few examples to prevent the corrosion, and method of corrosion is mentioned with suitable example. So illustration is mentioned how electron transfer takes place and how different type of ions are being produced. If you find any difficulty in these points, then feel free to ask, and if you don't have any confusion to these points in whole unit, then try to solve questions mentioned in exercise. And if you find any complicated examples, feel free to ask. We are going to discuss them step by step. Thank you.